And this comparison in my work between the observation and simulation is mostly to test the few of the observation and analysis pipelines, and also to develop few new methods that I shall describe. And our collaborators include Professor Christoph Federer and Dr. Ramesh Teta from Australian National University. So, just a brief introduction to ISM. So, it's very well known that if we equate the heating and cooling rates of the neutral ISM, we get two stable phases corresponding to warm and cold medium, and an unstable phase. And we expect most of the gas to be in the stable phases with the general understanding that there is a warm diffuse medium with the cold clouds inside. And the main pressure is obviously the 21 centimeter emission absorption from atomic hydrogen. And this kind of absorption emission spectrum, we generally consider it to be consisting of individual Gaussian components corresponding to the clouds along the line of sight, isothermal clouds. And if we decompose this spectrum into the Gaussian components and extract the components, radiative equation can give us the spin temperature and the column densities. But all the thermodynamic calculations that goes mostly involve the kinetic temperature, which governs the thermal motion of particles. But these kind of analysis doesn't give us the kinetic temperature because of turbulence, and we can't use the line width to get the kinetic temperature out of it. The basic reason is turbulence acts as a line broadening, and if we use the total width, we are surely overestimating the kinetic temperature. Now, is there a way to find the kinetic temperature? The answer, one such way was proposed by Otto Paul and Leopold in 2019, and that says that we can use the absorption spectrum, decompose it into the Gaussian components, and for each component we can use the turbulent velocity scaling law, which is how the non-thermal velocity dispersion scales with the length scale. And then we can couple it with the equation of states and the relation between spin and kinetic temperature as given by Linz in 2001. And then we can get the column density and corresponding kinetic temperatures. And given this, now we can compare how much gas is in what phase. And if we do that for observational data, we see that most of the gas, contrary to your expectation, finds themselves in the unstable region. Now, the main question is, can we test how reliable these inferences are through some method? And here where a simulation comes in. So I took the two-phase interstellar medium magnetohydrodynamic simulations performed by Sheta and Federer in 2022. The main description of the simulation is given here. Now, if we take the simulation box and generate absorption spectrum out of it and apply the Cole and Roy method with some necessary modifications that I don't have the time to discuss, we get this kind of distribution. This is what that method gives us, and this is what we this is the actual distribution that we expect. We see that though there is an overall two-phase distribution and what we get, there is clearly an overestimation of the higher unstable phase column density and underestimation of the warm phase column density. Now we go ahead to see what can be the possible reason for that. And one reason we found is there can be a lot of mixing between gas of very wide range of temperatures, and that breaks down the isothermal assumption of these components. And if we actually calculate the kinetic temperature of these sort of apparent Gaussian components, we get something in the intermediate range, though most of the gas may be in the warm phase in this blended component. Now, it is very difficult to test how much does it affect the actual observation data because of resolutions and etc. and the practical limitations associated with simulations. And the other standard limitations are because of the warm components have very low optical depth, we tend to miss in the Gaussian fitting, and also velocity crowding can be a major issue in something like this of blending of components. Now, these involves all these uncertainties in Gaussian decomposition. So we now see if we can do something similar with other data set that can give us some properties of the interstellar medium without going into any Gaussian decomposition and other uncertainties. So we turn to this brightness temperature and optical depth correlation plot, which says that if we take, this is nothing but taking the absorption emission spectrum pairs and just plotting the brightness temperature and optical depth at each velocity channel. Now, can we find a simple model for it that can give us some estimation of the physical properties of interstellar medium? And one model that I sort of came up with is this. So at the very low optical depth region, we expect mostly the warm gas to contribute. And we get this kind of an equation for brightness temperature, where TW is the parametric warm component temperature. And if we go to the sort of higher optical depths, we expect the cold components to come in. Now, as I am interested in the outer boundary for now, So the outer boundary corresponds to highest TB for a given term, and thus in my model I have put the cold component sort of behind the warm component and in the line of sight. The motivation being that the cold component radiation should not get attenuated much. And a bit of calculation shows this kind of expression for brightness temperature, where the parameters are C and TBW, where TBW is kind of a brightness temperature of the diffuse industrial medium in our line of sight. Now this fits the observation data there quite well, but this also fits simulation data quite well, but this also fits the observation data quite well too. Now, if we see how the parameters looks like for the simulation observation data, this is how it looks like. These are the properties that we can estimate from these parameters, and we see that these are sort of the parameters we get from the simulation observation. And one thing I did is I did not use the leads spin temperature kinetic temperature relation, and I forced these two to be equal to see how the parameters change. And we see that the brightness parametric temperature of the warm gas increases from 3600, which is expected. Now, a quick check is the typical optical depth of the warm gas, which we find to be quite reasonable here. And if we see how the physical properties that we can estimate, how these matches with the estimate and actual from the simulation, we see they're quite hopeful. And such modeling just shows we have the potential to give some physical properties of the ISM without getting into uncertainties related to Gaussian decomposition. And these are the observational estimates of the same. So I want to end with this, that my study shows that though something like that of Gaussian decomposition and all can give us qualitative description of the industrial medium, quantitative description suffers from incorrect estimation of the temperatures from any of the components, but we can bypass all that and find some way to get some estimation of the physical properties of the ISM without going into that, like modeling of beta. So thank you, and
thank you for being on time. So any questions?